All right, line W1, learning task number 7, we're going to go and take a look at inverter operations. And the inverter is going to be that necessary part that is going to go and take DC, and it is going to go and kick that DC back out as a synthetic type of AC. It is not going to be pretty AC, but it's going to be AC that we are going to go and see out of these. We're going to go through just some real simple little bits of inversion, and then we're going to go into our actual drive to what we have themselves. The very first thing that they show you over here is a simple mechanical switch inverter working off of DC. This is not a VFD, this is just helping us to understand how we can go and create current flow that is going to go and change its direction through something. Over here, if the switch is in that position, I see that I would be able to go and drive current through in that direction from negative to positive. And if I were to switch the switch down into that position over there, I would then be able to go and drive current through from negative through to positive of the battery. The alternate battery would get ignored, and so what we would see is that I would have current that would be traveling through from negative to positive. So for one of these, I'm going to draw with a different color marker because that's what I started with. So for this one over here, this would have to be negative, this would be positive at that point, and then the next alternation, when I switch this down over here, then this one over here is going to be negative, and this one over here would be positive. And what we see is that our load is seeing AC, seeing voltage that is changing direction going through it. We would call this a mechanical switch inverter. It can be done like this. It can also be done through the use of a single voltage source that would look like this. Let me just draw it here. Where I would take the load once again. I'm going to place the load inside of there, and then I'm going to go and have buses going to top, buses going to bottom, and I'm going to go and create what's going to be called a H-bridge, and the H-bridge is simply going to be two switches, switch and a switch over here, that would be tied together. It's easier to draw it like this, although it could be drawing it as a double pole switch that we would have, and then I'd have another switch over here, and another switch over here. And all that I would be doing with this, the H-bridge, see how it looks like an H? That's why it's called an H-bridge. Would be that, once again, I can go and close switch set A. We're going to call this switch set A. Or I can go and close switch set B. Call this switch set B over here. And I would be able to go and drive my current back and forth through here as well. Let's pretend that switch set A was the one that was closed. If switch set A was going to be closed, I would be able to pass my current through. There, we're just going to pretend like those are closed right now, and I would be able to pass it through like that. We would see that I would have current passing through over there. And if I had switch set B closed, I'm going to pass through in that direction. I'm going to pass through in the opposite direction. And so once again, we're going to go and have a load that would go and see AC through it. This is what we're going to be using. We're going to be using the H-bridge type because we're going to go and create only a single DC type of supply, right? We talked about that already in variable frequency drives that are made of three main sections. The converter, which is going to create DC, the filter, which is going to smooth out that DC and make it pretty, and then the inverter, which is what we're going to look at, that is going to go and feed that out. That would all take the place of this over here. If I were to go and move that. This would be my feeding out of my filter, and feeding my filter out of my converter, and then feeding that by my AC. So we'd go AC into converter, converter into filter, and then from the filter, I would take out the positive, negative, and then I'm going to go and switch it through a H-bridge. Okay. Our voltage waveform would look pretty square. It'd be pretty coggy sort of looking that we would have over here because it is going to go and have, it's going to be fully on in position number 1, then fully on in position number 2, then fully on in position number 1 again. And so what we'll see is this massive step to step to step and some really, really hard edges, right? Hard edges are always hard on our AC, right? It's dV over dt, really, when you take a look at it, right? Change in voltage over top of change in time that we are going to go and have. That is going to be quite significant, and that can be a bit of a problem for anything that's going to be electronic. It's also a problem for anything that's magnetic because we're going to have rapid changes in the amount of current that we're going to be forcing through stuff. This waveform will need to be cleaned up. What we're going to do is we are going to go and slow. You should remember that we've got a couple of components that will slow the rate of rise of something. I can go and slow rate of rise on the incoming like that. I can also use another component to go and slow rate of drop. So I can have a slow rate of drop, slow rate of rise. It kind of goes and switches, and we will be able to utilize those filter sections to clean this thing up. Now going back to our very first one here, the mechanical switch inverter, they then take the mechanical switch inverter a step further, and they say, well, we can do the mechanical switch inverter with 2 voltage sources with a single set of SCRs, but then they say, well, then we still have to have 2 voltage sources over here, and that's a bit of a pain. So why don't we just go with a single set of DC, and that's what they have over here, where they have now gone and created our classic H bridge using a single set of DC, positive over here, negative over here, and I'm going to be able to gate these things in alternate pairs. SCR 1 and 4, we're going to call that group A. SCR 3 and SCR 2, we're going to call that group B that we are going to have over there. And we can once again say that if we were to gate SCR 4 and SCR 1 simultaneously, what we would then get is current flow through following it. Let's do that. So we'll start on the negative side with A being gated on. We would just go and turn our current up through there. We would pass the load and we would pass our way out. And then when it would be B that would be put into conduction, we'd wait for A to finish its conduction. If it's going to be a large drive, we're going to use those GTOs, the gate turn off SCRs, and we'll turn it off. Otherwise, we wait for it to commutate on its own based on the holding current. And then we would go and apply signal to B, and we would see that B would then go in to travel up and out. Now, right now, we are just showing a simple load inside of here. We see that simple load is getting current through in 2 different directions, which means that it's AC. What we're going to do to replace this load is we are going to go and replace this load with a winding. And we're going to just do that with all 3 windings that we are going to go and have inside of our system, where we will run the 3 windings as loads through H bridges inside of these. All of our VFDs are going to go and follow this same type of a utilization path over here. We will get chopped up DC. Remember, we converted it from AC, we converted it into DC, and then all we did is we reversed the direction of DC that we were passing through there. So it's going to see what would in effect be a negative DC, and then it's going to go and see what in effect is going to go and be a positive DC that we would go and have inside of these. There is also going to be need for some inductive protection, right? Because we know that anytime that we have got coils, motor coils, they're inductors, and therefore they're going to want to collapse back in on themselves and create large induced values of voltages. And so we have to be careful that we don't allow that to go and take out a drive. As a result, what we will do is we will go and place in these inductors over here, what we're seeing, diode 1, 2, 3, and 4, and those are just going to allow us to go and forward bias any sort of a collapsing magnetic field. Right? Let's say that we had current that was traveling through, that we had changed this thing so it was now a winding, we'll draw it as a winding, and that we had current that was traveling through in this direction, which would mean that this would have had to have been the negative, this would have had to have been the positive. Then what we would see is that when we would remove that, this would try to maintain its inductor. It's going to collapse its field lines of flux in and around itself. It's going to try to maintain current flow, but it does so by creating its own positive and its own negative. And when it creates its own positive and negative, it's going to need a place that it can go and drive that positive back out. And so what we're going to do is we're going to go and have that connected over here so that when it collapses back in, guess what? It's going to go and feed its positive back into the bus over there. And this one over here is a diode as well, is going to go and feed its negative back into the bus as well. So we're not just dissipating the power off of these. We are going to go and actually put it back into our caps, into our inductor fields, that whatever we're using for our filtering. It's super handy. It's necessary so that we don't nuke stuff inside of there, but it's just really, really neat so that we see that we're just using the least amount of power as possible. All right, that's the waveform that we were going to get out of that one. We talked about that. Let's talk about now these things as a 3-phase bridge rectifier. The first of all, what I'm going to go and look at inside of here is that the motor connection internally itself does not matter. It could be Y, it could be delta. I really don't care what I've got inside of that motor. I'm just looking at the lines that I'm feeding out. And I'm really going to just check those lines and say, what is going to go and happen as far as me simulating AC off of those lines. What I'll see out of these is that I've got A positive, A negative, B positive, C positive, and I need to just take those values and I need to go and switch them at specific times. And actually, what I should do, just give me 2 seconds here. I'm going to go and take this drawing and I'm going to go and combine it with our next drawing that we have over here, because it just makes sense if we see those two at the same time. Because what this is going to show us is the way that we actually create a synthetic AC waveform out of here. What they're going to examine is going to be the voltage from A to B, the voltage from B to C, and the voltage from C to A. There should be a little A inside of your book next to that one. If there isn't, go and write the A in yourself. You've got pens, that's the technology that you need. Going through this one really quickly, because we're not going to go through every single step, what we do see is that the voltage is always in reference from one to the other. Subscript notation means that I'm standing on the last one. Remember, your shoes are the very last thing that you put on before you go out. Therefore, since shoes are the last thing that you put on, that's where you are going to be standing. That's the analogy that we use to take a look at in a double subscript notation. So when I'm standing on B looking at A, I'm going to see something. When I'm standing on C looking at B, I'm going to see something. When I'm standing on A looking at C, I'm going to go and see something as well. What we will see is just a switching sequence that we are going to go and apply to each one of these that is going to allow us to go and operate. Hold on a second. I'm just going to see, because I wasn't sure if there was another place that we covered this or if this was the only one. I thought we had one other place where this was covered. Yeah, no, there was a similar looking one when we were talking about rectification. I'm just confusing my two drawings inside of my mind. We are only ever going to have a single SCR gated on per phase. Okay, we should never have both of these together because then we would short out our DC bus. So we're always only going to be looking at a single one of these that's being gated on. The other one is inherently going to go and be off. So we're going to start with the very first thing that we see over here. The very first one, I see that my voltage A compared to my voltage B is going to go and be more positive. So I've only got two options, positive or negative. Therefore, this A would have to be at the very first step that we're looking at. Right over here, we're going to call that time 0 over there. A would have to be on, and my B negative would have to be on as well. And then if I take a look at B in relationship to C, so if I'm standing on C looking at B, I see that C is going to go and be more positive, right? From C looking to B, I see a negative. So therefore, the only option for C would be that. And looking from C to A, I see that there's no difference. See how it shows at 0 volts over here? That just means that there's no difference. Neither of those is going to be more positive than the other. That's how we get this beautiful little flat line that's going to be off of here. So for my very first instant over here, instant 0, I see that I'm going to go and have at instant 0, I'm going to go and have these ones here that are going to be gated. I'm actually just going to put the lettering up top over there. 0, 0, and 0. Okay, that's where I'm going to be gating at instant 0. The next thing would be what's going to happen at instant number 1. I want you to think about that each of these lines is just transferred down a little bit, so you're not trying to examine them on the line. Sometimes people just struggle with trying to translate them on the line because you're like, well, where is it on that line? Just move this line mentally just a millimeter or so over to the side over there, and that's really where we're analyzing. Number 1 is going to be right over here. At that point, we see that once again, in relationship to B, A needs to be greater. So at instant number 1, I can go and maintain that same thing. A needs to be greater at instant number 1. So B negative would be on, switching to the negative. A positive would be on, switching to the positive over there. If I take a look at my B compared to my C, I see that my B compared to my C is going to be at the same value of voltage. Well, I already know what B is switched to, therefore I know that C would have to be switched to the same thing. So I'm going to go and see that I'm now going to be switching my C to the negative over here. That's going to be step number 1. Step number 2, we're going to do the same thing. We're going to move this line over a little bit. I'm not going to start analyzing this one because that one's where they're both the same. I'm going to go to this one here. I see that my B is going to be more positive than my C. I'm standing on C looking at B. So if I'm standing on C looking at B, the only way that that could happen would be if this were to go and be my one that's turned on, B positive, and this were to also be turned on, C negative. And then at that point, I can go and analyze this line over here, and I see that my A and my B have got the exact same polarity because there's no potential difference. Therefore, that would tell me that A would be on over here. We'll do one more. After that, you guys are on your own to complete the rest of them. But if I go to my last one that I'm going to have over here that we are going to go and analyze into step number 3, I'm going to see that in relationship to B, standing on B, looking at A, I'm seeing a negative. So if I'm standing on B, looking at A to see a negative, that would mean that this would have to be negative. This would still have to go and be positive over here. And if I were to follow that one down, I would see that my C and my A have both got the exact same are the exact same polarity. Therefore, this would also have to be on there. You can step through the rest of them following the rest of the pairs. What you're always going to go and see is that if I'm looking at from step 0 to step 1, I see I have those 3. Inside of step number 1, I'm going to go and have 2 of them that are going to be the same. See, they're both on step 1, still going to be the same. And then one that is going to go and be different. And then moving on to step number 2, I would see that I'm going to go and, once again, I'm going to have 2 that are going to stay the same. So this one is going to go and stay the same. This one stays the same as my step 2. But now this one is going to be the one that changes. And so we're always just seeing just a single change at a time. You know, tick, 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 one at a time as they're changing over. And as a result, we get this approximation of a sine wave. You should be able to identify this as being a sine wave, and by the time that I would go and filter it, you would see that we would go and have, a sine wave that is going to look like that, another sine wave that is going to go and look like this, and another sine wave that is going to go and look like this. And we should see that they're all peaking at different times, 120 degrees apart inside of here. Let's talk about our main types of drives that we have right now. We've got VDI, we have got CSI, and we have got our PWM, which is going to be a voltage source inversion. We're going to talk about the VDI first. The VDI is a obsolete type of drive that we are going to go and have here. It does have a DC section that is going to be variable. I'm going to use the DC section with SCRs. This is going to change my amount of voltage that I'm going to go and have out of the drive, because that voltage is going to just change the DC that I'm sending out. This section over here is going to go and change the amount of frequency that is going to go and come out of the drive. Basically how quickly I'm going to chop up that DC voltage that I'm going to go and have inside of here. Inside of here on my filter section, what I'm going to go and have is I have got RC filtering over here, resistive capacitive filtering over here. There is a little bit of resistance that's going to be placed inside of here. It's going to be low ohmage, high wattage that it's going to go through here. Therefore, it's going to dissipate a little bit of heat. But what it's going to do when it goes through that resistance is it is going to go and give us an evener amount of power. We're also going to be charging up this cap over here. So this cap, every time that we raise, it's going to charge up, and then it's going to go and drop like that. It's going to raise, it's going to go and drop, etc. These ones also do have another subset that is going to be called the chopper drive that I'm going to go and have for these ones. That is just going to be just another method that we can go and send out voltage from these. Like I said before, though, these ones are becoming rapidly obsolete, if not, completely obsolete in a lot of places, just because they don't have, the best type of waveform that we can get out of them. They do put out a decent sort of waveform. If you take a look at these ones over here, we can go and get a waveform that looks like this. Once again, going and drawing the AC over top of there, you should see that we have got AC that is moving across here. We've got a single cycle, 120 degrees apart, that these things are all going to be peaking. As they go out of the drive itself, remember that the motor windings themselves are inductors. They're going to go and provide some smoothing as well. This one does provide for relatively simple VF, voltage to frequency ratio. Remember, we want to keep that VF the same so that we maintain our amount of torque. K is equal to K, or T is equal to K phi I cos theta, so we need to maintain those two together. As my frequency goes up, so as I chop more rapidly, I'm going to have to raise the amount of volts. Remember that the volts over here are going to be covered by my converter section, and that my frequency, the amount of time, is going to be contained by my inverter section. Those two are going to work together through the controls that we are going to have inside of here. They do show, a bunch of one-line diagrams for these ones, just once again showing that we've got the SCR adjustable DC supply that's giving my magnitude of voltage. I'm going to go and feed that voltage through here where I'm going to go and measure it. Feedback isolator just means that it's not going to be able to feed from one through to the other, but it's going to pass my signal through, so I'm going to measure that, and then I'm going to go and control that voltage. If it's too low, I bring it up. Too high, I'm going to bring it low. That's going to be my DC, my volts that I'm going to have, and then my frequency is going to go and chop and send that up. Both the converter and the inverter do require firing circuits, so complicated control that we are going to go and have inside of there. And both the voltage and the frequency are going to be controlled by wherever we are asking this motor drive to be for speed. We adjust both of those simultaneously. The next one that we are going to talk about, and we'll cover this one a little bit more inside of learning task number 9, is going to be my CSI. CSI is going to go and be a type of drive that is going to go and oppose changes in current. Once again, we are going to go and have DC sections that we are going to go and take in off of this one. We are going to vary the amount of DC, and then we are going to go and take that DC, we're going to feed it through an inductor. You should remember that an inductor opposes a change in current, and it does that by sticking magnetic lines around itself, and then it collapses those lines back in anytime that the current goes and changes, whether the current's increasing or decreasing. It fights it with that magnetic flux. So it's going to use as a predominant filter section a inductor inside of here. They're going to be heavy drives because large inductors to go and run 40-horse motors are going to be large coils of copper, size for a 40-horse motor, obviously. So we are going to go and have, a massive, massive amount of current that flows through them. They're going to be heavy drives. They will sometimes go and have another cap that's going to be on the downstream side that we are going to go and have over here. That cap on the downstream side is going to be used in conjunction, but because this is the first section that it hits, it's going to be predominantly current that is going to go and control out of here. That current CSI drive that we have is then going to once again take that DC and it's going to go and chop it up into our AC. And then every time one of these gates inside of here, this thing is going to slow down the rate of the rise of current through. So rather than it having a really square wave, it's going to have a nice smooth wave that it's going to be going through there, etc. CSI drives are going to be more reliable than the VVI drives. That's why they have, in a lot of cases, replaced them. Because we've got this massive inductor, inductors work off of collapsing magnetic fields, and it turns out it's really hard to break a magnetic field. So as long as your inductor's intact, your drive is going to go and stay intact. They both do have some disadvantages, VVI and CSI. And the big disadvantage of VVI and CSI is the fact that at low speeds, I get jerky motor movement. We call it cogging. It's almost like it's stepping through, gears as it's rotating, etc. We don't like to go and see that when we're starting up, that we kind of have those impacts. We'd rather see a smooth push all the way through. And we do have a fairly poor input power factor because we've got an SCR controlled DC section inside of each of these that's going to be chopping that up. And so we're not getting the entire waveform through on them. Just more obsolete types of drives. VVI for sure. CSI is slowly working its way out because we've got these other ones which are going to be known as my VSI, voltage source inversion. VSI. Okay, looking at this thing here, the current source inversion, what did we use as our predominant filter section inside of here? The current source inversion, we used an inductor because it opposes a change in current. On these ones over here, we are going to go and use a capacitor for a VSI drive. Now, they drew the filter section wrong inside of here. Don't get sad about it. Just, we know this is par for the course inside of our modules sometimes. But they drew the filter section wrong because our filter section should be primarily capacitive. Because what does a capacitor do? It opposes a change in voltage, right? It does that by, sending electrons away or from its plates, etc. So we are going to go and have a primarily capacitive driven, which means that we have a bunch of caps in the back. We will have some smaller inductors, but we don't have as large of inductors. Fewer turns. It's just going to be a final smoothing out that we will have. As a result, they tend to be lighter types of drives. They are sometimes quite bulky, but they are going to be lighter. They do also have voltage that we take in, and we maintain a constant amount of voltage. We don't need to control the DC section. We just rectify. We take everything in. We take everything in, stuff it back onto that cap. Once we stuff it onto that cap, then we can go and take it out to our AC section. We are going to go and have different types of switching often. This is the more modern one. We're going to have transistor switching, primarily IGBTs at this point, that we are going to switch out to the motor. And what we do is we switch out the full value of voltage to the motor. But we do it in little pulses. That's why we call this thing PWM. If I go to average, the amount of voltage, this tiny spike of voltage with this absence of voltage, I would get a very low value. And all that we're doing is we're averaging the amount of volts that I have versus the amount of time. We will always see, no matter how much power we're trying to put out, we will always see a pulse right at the very beginning of the waveform that we're going to have. Doesn't matter whether we're going low power or not. If I was going to go for my absolute lowest power, I would have just a spike at the beginning and then nothing. And then I'd have a spike in the opposite direction and then nothing. And that would go and give me overall a very, very low average, but I need to have that spike because that's going to go and give me my frequency that I'm going to go and have. What I do then is I just apply more spikes. More spikes means that I've got more averages that are going to be high value of voltage compared to values of 0 over here, and therefore my average value of voltage. And all that the PWM-driven load is looking at is it's saying, over the last couple seconds, what's my average? Okay, then I'll put that in as being my average. And then if I use the same measurement over here, now I see that I'm going to have a higher average. And then if I use that same measurement over here, I'm going to go and have a higher average. And then I use that same measurement over here, and then I would go and see a higher average. And that's how we get this synthetic AC that's going to come out. Now, it's a real jerky, bang, bang, back and forth like that. But that's fine. We're not that concerned about it because we do have, once again, the filtering action that we are going to go and have of our motor coils, as well as the filtering action that we are going to go and have of our small set of inductors inside of the filter section, right? Because we're going to be stuffing that back through there as well. There is a more complicated type of VSI drive that is called the Flux Vector Controller. And the Flux Vector Controller basically monitors the amount of consistent current going out to go and flux the stator windings compared with the pulsating flux that's going out, which would be obviously what it must be transferred over to the rotor windings. And it goes and sends out different values of voltage, different values of time to go and maintain a consistent flux on there. It just monitors both the rotor and the stator flux independently, and then it can go and maintain a much better amount of torque is really the big reason that we like to go and see those flux vector drives. Expect to see a lot more flux vector drives in you guys' careers, probably a lot more than what I saw inside of my career because they were still too pricey. We liked them, we wanted them, but we could not always convince the customer that that was the drive that they should be buying. All right, we're going to cover a bunch more of the, fine-tune this stuff in our last learning task for our variable frequency drives.